Okay, so welcome back. So this is the third session. So in a brief recap of a previous session, so we looked at what a system was. We described the function of a system mathematically, that it is nothing but it takes the signal x of t, transforms it and gives the output y of t, right? It acts on the input signal x of t and gives the output y of t. And we looked at one important property of the system, right? So based on the relation between the input and the output. Okay, so if a system's input output relation satisfies the two principles, the principle of homogeneity as well as the principle of superposition, so we say that the system is a linear system. Okay, so it satisfies the linearity property, hence we say that the system is a linear system. So from there I gave an illustration of an ideal amplifier of gain 3. Okay, and we looked at this amplifier and we saw that it satisfies both the principle of homogeneity as well as superposition. So the amplifier is basically a linear system. Okay, so and we saw the another example, right? I just gave an example and I told you to prove that the system is non-linear. So where the input output relation was the output y of t was equal to the square of the input signal x of t. Okay, you can see that both the principles are not satisfied. If one of the principle fails, if the system fails to satisfy one of the principles, then we say that the system is a non-linear system. Okay, so we don't go to check another one. So in this case, since if you're interested, you can check both the properties. You can see that both the properties will not be satisfied anyway, right? So moving on. So before I define the property of time invariance, I want to tell you what time shifting is. Okay, suppose say I have a signal x of t is equal to some cos 3 pi t. Okay, let's say I have this signal, right? So where the frequency f is equal to 1.5, right? So you know the relation omega is equal to 2 pi f, right? So 2 pi f radians per second, right? So if you look at this, so when you compare, you get f equal to 1.5 hertz. Okay, now suppose what I'll do is I'll shift it by t minus, let's say to get pi by 2, so 1 by 6. Okay, right? So let's plot these signals. Okay, we'll plot x of t as well as y of t and we see what the relation between them is. Okay, so this is basically, this operation is called as the time shifting operation. Okay, right? So I know what a cos signal looks like, so I'm going to draw the cos signal as it is. And to keep things simple, I took the amplitude to be equal to 1, right? So at t equal to 0, it's 1, right? Okay, so this is how it looks. So this point here is minus 1 and this point here is plus 1. Okay, and this is t equal to 0 and you have the same signal on both the sides. Okay, right, so on and so forth. Okay, and what is this value? This is when your 3 pi t is equal to pi by 2. So 3 pi t equal to pi by 2 implies 3 t equal to half, right? So t equal to 1 by 6. So this is your 1 by 6. This, I guess it's 2 by 6. Okay, and 3 by 6, so on and so forth. Okay, so you can calculate that. Fine. I'm writing this randomly, please verify this. Okay, so this is my signal x of t. Okay, now if I keep the origin same, right, the reference point the same basically, so let's say let's see what the relation between x of t and y of t is. Okay, so I have this x-axis, this y-axis, t. Okay, So when t equal to 0, so my here, so when you substitute t equal to 0, what do you get? So my y of t, right? So why am I writing y of t not y of t minus 1 by 6? Because the variable only is t, right? So anyway, it will be a function of time. I'm just calling it by a different name, right? Okay, so it's basically I'm shifting the function, right? And my variable will be t, so my axis is t here, as you can see, and this is y of t. Okay, so 1 by 6 is a constant anyway. Okay, my at t equal to 0, what will my y of t at t equal to 0 be? Okay, so now cos of 3 pi into t minus 1 by 6, because it is x of t minus 1 by 6. So if we do this, and what do we get? We get cos 3 pi t minus, right, 3 by 6 into this one, so I get pi by 2. Okay, so at t equal to 0, what do I get? At t equal to 0, I get cos of minus pi by 2, and cos of minus pi by 2 is 0, right? So I'll get 0. At y of t at t equal to 0 is 0, right? So I can do the math. At t equal to 1 by 6, what do you get? So at t equal to 1 by 6, you get cos of pi by 2 minus pi by 2, which is cos of 0. So I'll get 1. Okay, here. Right, so this is what you get. Okay, so you can plot it, and I suggest you to please plot and try. Okay, so what I did was I selected the appropriate value of the shift, and here we can see that I shifted the cos signal by pi by 2 radians, and of course when you shift cos by pi by 2, the signal that you get is a sine waveform, and we are seeing it. Indeed, that's the case here. Okay, so what did I do? So I basically took the cos signal. So when I keep the reference same, it's as if I have moved the cos signal 1 by 6 units to the right. Okay, so if you move this signal, the cos signal 1 by 6 units to the right, okay, so you get the signal at the bottom. Okay, so if the sign was plus here, you would have done the same thing, right, except that you would have moved the cos signal to the left. Okay, this is just the layman's talk, right? So this is how you get the waveform, right? So you substitute for t here, right? Instead of t, you substitute t minus 1 by 6, and when you do the arithmetic here, so you get the relation between y of t and x of t. Okay, and when you plot y of t with respect to t, you get the signal that is shown in the second diagram. Okay, so this is basically the time shifting of a function, right, by the appropriate units. Moving ahead, so what do you mean by the term time invariance? Okay, so time invariance is not defined with respect to a signal. It is a property of a system. Okay, time variance or time invariance is a property of a system. Okay. Now, okay, so to define time invariance, right, so we'll take a system. S, okay, I feed x of t and note down what the output y of t is, and in shorthand notation, this is my system S takes the input x of t and gives rise to the output y of t. Now what I'll do is I'll keep the system S the same, okay, and what I do is I shift the input, okay, by some units, right? So let's say I delay or advance this. So basically what we did in the previous case here with the x of t minus 1 by 6, I delayed the cos signal by 1 by 6 units. Okay, so it's called delaying, right? Time shifting has two parts. One is delaying when you move the waveform to the right, and if there is a plus sign in between, you would have noticed that the waveform would have moved to the left. Okay, so that would be advancing. Okay, with respect to origin, the waveform is getting delayed or advanced. Okay, so that is what the meaning is. Okay, so now what I do is I time shift the input, okay, by tau units, and I pass this shifted input through the same system S. Okay, so if the output, I note down what the output is. Okay, let's say the output be y1 of t. Okay, and now I will study the relation between these two. Okay, if y1 of t, the output when you send the time shifted input, right, if you look at the relation between these two, if y1 of t is the same time shifted version of the same output y of t, right, we say that the system is time invariant. Okay, right, so that is what, if t is the unit of t was days. Okay, so I take a system S, right, I pass x of t today, right, I note down what the y of t, the signal y of t is. So if tau is equal to 1, since the unit is days, so x of t minus 1 corresponds to delaying the input by 1 day. Okay, which means I take the same input x of t, instead of passing it through the system S today, I will pass it tomorrow, right. So if I get the same output, okay, y of t, right, the next day also, which means it will be y of t minus 1, right, the system is time invariant. Okay, it's behaving the same way today as it behaved the same way tomorrow, right. So the system is said to be time invariant. This is a broad sense. So the units of t can be seconds, microseconds, milliseconds, whatever, depending on the context. So I just gave an example taking the units of t as days. Okay, so an example will be a resistor, right. So not going through the so much sensitivity. So a resistor, if it's 1k today, tomorrow also it will be 1k in broad sense. Okay, so don't go into depth. Okay, so a resistor will be a time invariant system. Okay, so I'll stop here.